Each time the young lady in this video applies a force to the wheel that's in her hand, the wheel applies a force on her hand in the opposite direction. This is a perfect illustration of Newton's third law. The common definition for Newton's third law is that for every action there is an equal but opposite reaction. There's actually a better definition, but we'll get to that later in this presentation. A skater glides across the ice by applying a force on the ice in the direction that is exactly opposite to where she would like to travel. She applies a leftward force on the ice, and the ice applies a force on her that is equal but opposite in direction. A car moves to the right because its tires apply a force on the road to the left. These forces are often called action-reaction pairs, but perhaps it's more accurate to call them interactions because the action and reaction are simultaneous. Let's look at some third law interactions. The explosion in a rocket applies a force to move the rocket forward, and the rocket applies a force that pushes the exploding gases in the opposite direction. When you let the air out of a balloon, the balloon applies a force on the air, and the air applies an equal but opposite force on the balloon. When you try to tighten a bolt in space, you become very aware of Newton's third law. You realize that when you give a force, you get a force.
When an astronaut goes to turn a bolt on a space station, or any spacecraft, the bolt's not going to go anywhere. They're just going to spin around the bolt. Which we found to be sort of fun, but not very productive. So the astronaut's got to find some way to hold themselves back to the spacecraft, or they'll just float around. Think of this as my spacesuit. I can do light tasks by holding on with one hand, or heavy work clicking into a foot restraint, or medium tasks by clicking into a device like that, hooking up to the spacecraft and rigidizing.
Let's see if you can apply what you've learned. All the forces in the universe would be an odd number, an even number, or unknowable. There are an even number of forces in the universe because whenever a force acts on an object in one direction, another force acts in the other direction. Remember, forces always come in pairs. As I said before, the common definition of Newton's third law is that for every action, there is an equal but opposite reaction. I like what Newton said about the third law. When you press on a rock, the rock presses on you with a force that is equal but opposite. I believe the definition of Newton's law that produces the deepest understanding is that when object A exerts a force on object B exerts an equal force on A, but in the opposite direction. The toughest part of the third law for most students to understand is that in all third law interactions, the forces are equal. I have a few videos that will help you see this. These videos were made by a terrific high school physics teacher named Frank Noschisi, who lives in New York State. Each card shown here has a metal hoop that compresses during the collision. Notice that each loop compresses by the same amount, which indicates the forces that each card experiences is equal. In this interaction, once again, the hoops compress the same amount. People often mistakenly believe that the stationary body receives the greater force. A person watching a hockey player check another player that is stationary often believes that the player who is not moving received the greater force. Let's look at the loop compression in this interaction. Will the forces be equal in this interaction? Once again, the hoop compressions show that the forces are equal. A lot of people believe that when a truck hits a stationary or small stationary car, the car receives the larger force. This, of course, is not true. In this video, the more massive card is now at rest. Look carefully at the steel hoops again. Once again, the results are the same. The forces that the masses apply to each other are equal but opposite. Most people viewing this interaction would assume that the card on the right received the greater force because it received a much larger acceleration. If we go back to our definition of inertia, we might make better sense of what we are seeing here. Inertia is an object's resistance to a change in motion due to its mass. The smaller mass cart has less inertia and therefore has a smaller resistance to a change in motion. If two bodies receive the same force, the smaller mass would always have a greater acceleration. Remember, you can't determine the force on a body just by looking at its acceleration. Remember, F net equals ma. To experimentally prove that the forces that each body exerts during an interaction are equal, we could simply multiply the mass of each body times the acceleration. Large masses will experience a lower acceleration when they receive the same force as a smaller mass. Newton's third law also applies to stationary objects that are in contact. When a 10 Newton lamp rests on a table, it applies a 10 Newton downward force on the table, and the table exerts a 10 Newton upward force on the lamp. When you sit in a chair, your downward force on the chair is equal to the chair's upward force on you. The third law of motion applies to forces like gravity and electrostatic forces. For instance, we all know that the Earth applies a downward force on our body, but that's not the whole story. It's also true that you apply an upward force on the Earth. It's not obvious that you apply a force on the Earth because your force has such a negligible effect on the Earth's motion. The reason your force has such a small effect on the Earth's motion is because the Earth has a tremendous amount of inertia. The Earth has a large resistance to a change in motion due to its large mass. In this presentation, you've learned that forces come in pairs, and that when object A exerts a force on object B exerts an equal force on object A, but in the opposite direction. This is the end of my presentation on Newton's third law.